Hi everyone, I'm Qingtao, and today I will be presenting our work, Probability Density Geodesics in Image Diffusion Latent Space. A pre-trained diffusion model learns the gradient of data distribution in the latent space, which reveals the underlying structure of the space. Now let's imagine that these 2 points in the latent space represent 2 images. A video transitioning smoothly between them corresponds to a path in the latent space. But here is a question: what makes a good path? At first glance, a straight line might seem like a natural choice, but when we sample images along this path, the results are often low in quality. This happens because the straight line cuts through regions of low probability density. Instead, we aim for a geodesic path, one that remains direct but curves to high density regions, preserving image qualities along the way. To compute such a geodesic, we first define the length of a path gamma as an integral over a cost function along the path. The cost function is a Riemannian metric. We formulate it as the Euclidean velocity weighted inversely by the probability density at each point. We then compute the functional derivative given this path length definition. By minimizing the functional derivative, we can optimize the path to geodesic. We use the score distillation function of the diffusion model to estimate this nabla log p gamma. Here is a 2D toy example. Starting from a straight line, we perform the optimization, and the path is pulled towards regions of higher density. We also visualize the probability density along the path and observe a clear increase after the optimization. Now, we apply this method to the latent space of a pre-trained image diffusion model and explore 2 applications. The first one is image interpolation, which can be formulated as solving the boundary value problem. Given 2 input images, we compute the geodesic path that connects them in the latent space and sample along this path to generate smooth, high-quality intermediate images. The second application is image extrapolation. Starting from a single input image and an initial velocity guided by a target prompt, we generate a sequence of images with the desired transformation. In the first part of the experiment, we aim to test whether video clips are approximately geodesic. To start with, we first generate a large set of short videos involving variations such as camera motion, object attributes like locations and colors, and environmental factors like lighting. For each video, we compute the magnitude of the functional derivative along its latent path and compare with several baselines, including the perturbed by different amount of noise and the over-smoothed version of the path. Both of them increase the fundamental derivative and get far away from the geodesic. We then apply a few iterations of our geodesic optimization. This leads to a reduction in the gradient magnitude, suggesting that the original paths are already close to the geodesic, but can be further improved through optimization. We perform this analysis across all video clips and summarize the results. On average, the same conclusion holds. Then, we conduct experiments to show the effectiveness of our applications. We begin with the image interpolation. Given 2 input images, we optimize the geodesic path between them to generate smooth and high-quality intermediate frames. We also conduct experiments to analyze how the path probability and path length evolve during the optimization process. As the path is optimized, we observe an increase in relative probability along the path, alongside a decrease in our defined path length. Last but not least, we present results for image extrapolation, starting from the single input image and an initial velocity which is estimated using a target prompt and a heuristic function. The result image sequence shows smooth transformations and align with the target prompt. Thank you for watching, and here are our GitHub page and contact email.